Alright, so you see what we did last class was to define the notion of a morphism, and the idea of a morphism is that it is a continuous map which should pull back regular functions to regular functions. Okay, that is the definition of a morphism. And then I stated a few results. Let me recall them. So let x be any variety. In our case it means either it is an affine variety or quasi-affine variety. An affine variety, as you know, is an irreducible closed subset of affine space, and we are working over an algebraically closed field. Okay, and a quasi-affine variety is a non-empty open subset of an affine variety. And variety for us at the moment means either an affine variety or a quasi-affine variety, which means either an irreducible closed subset of affine space or a non-empty open subset of an irreducible closed subset of affine space. And we saw that if x is affine, okay, then then Ax and Ox are isomorphic. Okay, so Ax is the coordinate ring of x, the ring of polynomial functions on x, which is gotten by taking the ring of all polynomial functions of the affine space in which x is sitting inside, modulo the ideal of x, which is a prime ideal, and Ox is supposed to be the ring of all regular functions on x. Okay, and we saw that if x is an affine variety, then there is an isomorphism like this. Alright, and mind you, this isomorphism is not just an isomorphism of rings, it is an isomorphism of k-algebras. Okay, it is an isomorphism of rings which is also an isomorphism of k vector spaces. Okay, it is a k-algebra isomorphism. And of course Ox was defined to be the ring of regular functions on x, and regular functions were defined to be functions which were locally given by quotients of polynomials. Okay, now we then I told you that we defined then the notion of a morphism of one variety into another variety, and what we did was we showed the set of morphisms of varieties from x to a1 or let me put y to a1 is isomorphic or let me again put x or let me put y. Okay, y to a1 is isomorphic. It can be identified with oy for any variety y. Namely, every regular function which is a map from y to k, okay, is the same as a morphism from y to a1, where k is thought of as a1, which means that a1 is just k with the Zariski topology, and the Zariski topology there of course is, you know, it is a complement finite topology. It is a topology for which the open sets are complements of finite sets, the closed sets are only finite sets. Okay. So, and I told you that this this can be generalized, that this statement can be generalized. So, you know, this statement can be written as morphisms of varieties from x. So let me go back to so let me again write y to a1 is isomorphic to this, can also be written as morphism of k-algebras from O of a1k to O of y, because this O of a1k is actually isomorphic to kx. O of a1 is just the O of a1 is the same as a of a1, okay, and a of a1 is k of x. It is a polynomial ring in one variable. Okay. So if you want I can write. I'm using the fact that, you know, O and A are the same for an affine variety. So if you want, I'll write this can be identified with A of A1, and that is isomorphic to kx. Okay, and the all possible k-algebra homomorphisms from the polynomial ring kx to any k-algebra is in bijection with the elements of that k-algebra, okay, because this is the universal property of the polynomial ring in one variable. Okay, namely any k-algebra homomorphism from kx to oy is completely controlled by what? By the image of x. Okay, it is controlled by the element of oy that x goes to. Okay, and therefore you will have as many k-algebra homomorphisms as there are elements in oy. So this set is the same as oy. Okay, so I am just translating the statement like this using the universal property of the polynomial ring in one variable. And then I told you that more generally you can also write it as what I have written for a1, you can write it for an, and not only for an, you can write it also for any affine variety. Okay, so the statement is morphism of varieties from y to an can be identified naturally with morphisms of k-algebras from O of A, from A of an to oy, and what I can do for a1 and I have done for an, I can do it also for an irreducible closed subset of an, namely an affine variety. So I can also write it as morphism of varieties y comma x is isomorphic to is in a natural bijective correspondence with morphisms of k-algebras from A of x to oy. Okay, where of course x is of course an affine variety. Okay, So this is the most general statement, okay. So in this general statement, if you put x equal to an, you get this statement. If you put x equal to a1, you get this statement, which actually, so if you put x equal to a1, it boils down to this statement, that regular functions are nothing but morphisms into a1, okay. Regular functions are no different from morphisms into a1, right. So what I am going to do is, this is a very important statement, okay, because as I told you at the end of the previous lecture, that this is the statement that gives an equivalence of categories between on the one side the category of affine varieties with morphisms being morphisms of affine varieties, and on the other side the category being the category of finitely generated k-algebras that are integral domains with morphisms being k-algebra homomorphisms. So what I am going to do is I am really going to focus on proving this fact, okay. So that is what I am going to do now. It is a very important fact. So proof of the statement, morphisms, let me rewrite it again, varieties from y to x, isomorphic. Here of course this means there is a bijection of sets, okay. This what you have here is a set, what you have there is a set, but the point is that this side represents the geometric side, the algebraic geometric side, this side represents the commutative algebra side, okay. And as usual, whole point about algebraic geometry is that you go from the from the geometric side to the commutative algebra side. This translation is very important in algebraic geometry, okay. So what I am trying to do is I am trying to prove this. This is the algebraic geometric side, morphism of varieties from y to x, and here is the commutative algebra side, which is morphisms as k-algebras of ax to oy. So this is what I am going to prove, okay. So I am going to prove that there is a bijection like this, there is a natural bijection like this. Now how do I do that? So define alpha from morphism. So again let me write this down. I define a map like this first. I define a map like this, which is if you give me a morphism phi of varieties from y to x, this is an element on this side, I have to send it to something here, and you know what I am going to send it to here is a very natural thing. It's the thing that characterizes what a morphism is. A morphism is a continuous map which is supposed to be considered as a pullback map, something that pulls back regular functions to regular functions. So what I am going to do is I am going to just take the pullback via phi of regular functions. And what does that mean? It means, so the notation for that is phi upper star, which is a map from regular functions on y to regular functions on x, okay. So this is my map. So what is it that is happening? If you give me a regular function f on y, I get the pullback of that regular function to x is a regular function on x. This is the defining property of a morphism apart from its continuity. And what does this mean? This is just composition. So you know you have y to x, you have this map, you have this morphism phi, and f is a regular function on y. I have messed up x. I have mixed up x and y. This should be x and this should be y. So you have a regular function on x. F is a regular function on the target. So it's if you want f is a morphism into a1 or it's a regular function into k, okay, and then what is a pullback? It is this map which is a composition. This is first apply phi, then apply f, okay. This is otherwise called as phi upper star of f. This is the pullback, and the fact is that if you have a regular function on the target, by composing with the morphism you should get a regular function on the source. The target is x, so give me a regular function on x. By composing with phi, the pullback will be a regular function on y. This is the definition of a morphism, okay. This is part of the definition of the morphism. And mind you that this Ox can be canonically naturally identified with Ax. In fact, I should even put equality, okay. Ox is the same as Ax, right. So here also when I say that if x is affine, then Ax and Ox are isomorphic, in fact you can say that they are equal, okay. If you think of them as functions into k into a1 with which is k with the Zariski topology, they are equal actually. So there is actually an equality here, right. And so it is very clear that I have a very natural map. Given any morphism, look at the pullback map which takes regular functions to regular functions, and it is very easy to see that this pullback map is of course a k-Algebra homomorphism, because you know phi upper star of f1 plus f2 will be phi upper star of f1 plus phi upper star of f2, and phi upper star of f1 into f2 will be phi upper star of f1 into phi upper star of f2. You can easily verify that this what you get here is not just a map from Ax to Oy, but that is a k-Algebra homomorphism, because functions, by the definition of functions, everything is done pointwise. Sum of two functions is defined pointwise, product of two functions is defined pointwise, multiplying a function by a scalar is a new function which is also defined pointwise. So you can easily check that this is certainly a k-Algebra homomorphism, okay. What we need to prove is that this map, I have written alpha, but well, so this is alpha of phi, but the better notation is phi upper star, okay. But since I have written alpha here, I will also write it here, alright. And what will I have to prove? I will have to prove that this map is injective. I have to prove this map is surjective. That is all I have to do, alright. So let's try to prove the injectivity. Let's try to prove the surjectivity. So I guess the injectivity is very easy. So what is the situation? Suppose I have two morphisms which give rise to the same k-Algebra homomorphism as pullbacks of regular functions, then I have to say that these two are the same, okay. So suppose alpha of phi1 is equal to alpha of phi2, which is the same as saying that you know phi1 upper star is the same as phi2 upper star, okay. I will have to show phi1 is the same as phi2, right. We need to show that phi1 is the same as phi2. So you have to show that these two morphisms are one and the same. And what do you mean by equality of morphisms? By equality of morphisms means equality of the underlying maps as sets, okay. Equality is just as set theoretic maps. So it is a set theoretic checking that you have to do, okay. So how do I check two maps are equal? I check two maps are equal by evaluating them at every point and showing that they are equal. So what I do is well, so here is my situation. So I have y, so there are these two maps phi1 and phi2 which are morphisms into x, and mind you x is an affine variety, which means that x is sitting inside, x is an irreducible closed subset of a suitable an. So let us consider that it's sitting inside, it's an irreducible closed inside some an, okay. And let's let's put coordinates on this an, okay. Let me say with coordinates t1 etc. tn, let these be the coordinates on an, alright. So when I say an with coordinates t1 etc. tn, what it means is that I am just saying that if you take the ring of polynomial functions on an, I am identifying it with k polynomial ring in t1 etc. tn, okay. This is what it means. The choice of variables in the ring of polynomials in an, those variables, the choice of variables will also give you the labels for the coordinate functions, okay. And what happens is that, you know, this is an irreducible closed subset, therefore this, if I go mod the ideal of x, which is going to be a prime ideal, I am going to get a of x, okay. So it's going to be so this is the polynomial functions on an restricted to x, okay. To get the ring of functions on x, I will have to go modulo the ideal of x, which means I will have to identify two functions on x if and only if they differ by a function that is 0 on x, and that identification corresponds to going modulo I of x, okay. And so, you know, under this map, you know, all the every xi, any ti will go to some ti bar, okay, if you want thought of as an element here, okay. And mind you, ti bar is geometrically ti bar is just the coordinate function ti restricted to x. So this ti bar is just ti restricted to x, okay. Actually, what is this quotient map? Given any polynomial, consider it as a function on the affine space and restrict it as a function on x, that is this quotient. This quotient map is actually restriction, geometrically it is restriction of polynomials to a closed subset, this closed subset x, okay. And how do I check these two maps are equal? I check these two maps are equal by looking at the image of a point. So let me take a point small y, okay. The point small y will go to under phi1, it will go to phi1 of y, and which is a point, it's going to be a point of x, and under phi2 it's going to go to phi2 of y, which is a point of x again, okay. And both phi1 of y and phi2 of y are going to be points in affine n space, so they are going to have coordinates. So let phi1 of y be, well, lambda 1 etc. lambda n, because it's a, after all phi1 of y lies in x, and after all it's a point in n space, it is given by n coordinates, okay. And phi2 of y is, say, given by mu1 etc. mu n, these are the coordinates of this point, okay. And what I will have to prove is that if phi1 upper star equal to phi2 upper star, then I will have to show that these lambdas are the same as the mu's, which will say that the point phi1 of y and phi2 of y are one and the same point, and if and since y was arbitrary, it would tell you that phi1 and phi2 are one in the same map, okay. So so the point that one has to understand is that what is the meaning of phi1 upper star equal to phi2 upper star. So phi1 upper star is the pullback map from the ring of functions on the target, the regular functions on the target, to the regular functions on the source. So it is from ax to ay to oy. Of course ax is the same as ox because x is affine, okay. So this is the pullback map, okay. And what does the pullback map do? Given a function, given a regular function on x, I compose it with this to get a regular function on the source. That is how the pullback map works. Take a regular function on the target, compose it with the map you get a regular function on the source. So so in particular, you know, the TI's, okay, restricted to x, they are also regular functions on the target. Mind you, AX is the same as OX because x is affine. So these TI bars, they are regular functions on x, the coordinate functions. They are just the coordinate functions on the affine space restricted to the irreducible closed subset x. Okay, so if I take each of these TI bars, which is the same as TI restricted to x, they will go to this. It will go to phi1 upper star of TI. Okay, and what is given to me is phi1 upper star is the same as phi2 upper star. So what it means is that phi1 upper star equal to phi2 upper star means that this is the same as phi2 upper star of Ti bar for every I. This is what it means, this is what is given to me. Okay, now just think for a moment, what is the meaning of phi1 upper star of Ti bar? Phi1 upper star of Ti bar is the regular function on y which is gotten by pulling back the regular function Ti bar on x. And what does pullback do? Pullback is just composition with phi. So what this means is, it means that phi upper star of f, as you see, phi upper star of f is f circle phi. Okay, it's just composition. So if you translate that, you will get Ti bar composition phi1 is equal to Ti bar composition phi2. This is true for every I. This is what it means. Now this is an equality of regular functions on y, so apply it to the point small y. So what you will get is Ti bar of phi1 of small y is equal to Ti bar of phi2 of small y. So this will tell you that Ti bar of phi1y is equal to Ti bar of phi2y. Okay, but phi1y is phi1y has these lambdas as the coordinates, phi2y has mu's as the coordinates, and if you take a point like this, the action of Ti bar on that point is to give you the ith coordinate. Okay, it is just the function Ti on affine space picks out the ith coordinate of the point when you evaluate it at a point. So if you do that, what I am going to get is that I am going to get lambda I is equal to mu I, and this is going to be true for all I, and this implies that phi1 of y is equal to phi2 of y for all y in y, and that tells you that phi1 equal to phi2. Okay, so if alpha of phi1 equal to alpha of phi2, then you get phi1 equal to phi2, and that is injectivity. Okay, okay. The slightly more involved part of the proof is the surjectivity, namely to show that if you give me a k-algebra homomorphism from Ax to Oy, it arises from a morphism. Okay, and of course once you prove it arises from a morphism, we are already saying that that morphism is unique because we already proved uniqueness, that is the injectivity. Okay, so surjectivity is what we have to see next. So how does one do the surjectivity? So so what I am going to do is I am going to start with, so here is my situation. I have these morphisms of varieties from y to x. I have this map alpha, and on this side I have morphisms of k-algebras from Ax which is the same as Ox to Oy. Okay, and I am trying to prove surjectivity of this map. I have already proved injectivity. So what I do is I start with the k-algebra homomorphism zeta. Okay, so zeta, I start with an element here. Zeta is a k-algebra homomorphism from Ax to Oy. I start with the zeta, and I am trying to show that there exists a phi such that alpha of phi, namely phi upper star, is the same as this zeta. This is what I have to prove. Okay, but what is Ax? Ax is, if you look at it carefully, Ax is just kt1 Tn mod Ix. Okay, and so this Ax is just k T1 etc. Tn mod Ix. Okay, this is what it is. In fact, so it is k T1 bar etc. Tn bar. It is generated by the images of the Ti's. Okay, it consists of just polynomials in the Ti bars. That's all. Okay, and so in particular, you know, you have these elements Ti bars, which as you know are just the polynomial functions Ti restricted to x. Okay, and what you do is you take their images under zeta. They will go to some you know, let me look at it for a moment. They will go to some Fi's, and these Fi's will lie in Oy. Okay, see, after all, the Ti bars are regular functions on x. Okay, and zeta is a ring homomorphism. It's a k-Algebra homomorphism, so it's going to take an element here to an element here. So if I take Ti bar, it's going to give me an element there, and what is an element there? It's a regular function on y. So Fi is the image under zeta of the Ti bar for every I. Okay, so the moral of the story is very simple. The moral of the story is, the moment you give me a k-Algebra homomorphism from Ax to Oy, the n coordinate functions on Ax, which are actually the n coordinate functions in the affine space in which x is sitting restricted to that x, they automatically give you a bunch of n functions on Oy. Okay, what does it mean to give you n regular functions on Oy? It means that you are giving n maps into k, n scalar maps into k on y. But that means what you are trying to do is, if you think about it, for every point of y, if you evaluate these n maps, you are getting an n tuple of points. Okay, so you can see that this should give you a map from y to a point to an, and that will be the map that will be the morphism that you are looking for. Okay, that's how you get this surjectivity. So we will have to use these Fi's to define a map from y to an, okay, by simply evaluating a point of y at these Fi's and putting them as coordinates. Okay, so you will get a map from y to an, and then we will easily see that the map will actually factor through x, and we will prove that the map is a morphism, and we will prove that the alpha of that map is zeta. Okay, therefore we will get the surjectivity of zeta. Okay, so let us do that. So what I am going to do is, let me rub this side off. So I mean, what you should remember is that the moment you are given n regular functions on a variety, you must always remember this. Whenever you are given n regular functions on a variety, you are actually given a map of that variety into an. This is the idea. Okay, so let me write this down. Define phi, let me use psi, from y to an by y going to f1y fny. Okay, this is a well defined map, because the Fi's are all regular functions on y. If you evaluate a point of y at any of the Fi's, you are going to get a scalar. You are going to get an element of k, and this is an n tuple of elements of k. So it is a point in an, which is just kn with a Zariski topology, and here is my map. Alright, now the first claim is that psi maps into x. The first claim is that psi maps into x. This map is not just going into an, but it is going to go into the irreducible closed subset x of an. It's going to go into this irreducible closed subset. That's because it came from zeta, as you will see. So how do I show psi maps into x? So it's very simple. So what does it mean to how does one verify this? You have to show that given a point of small y, given a point small y of capital Y, the corresponding point psi of small y is a point of an which actually lies in x. This is what you will have to show. But how do you show a point of an affine space lies in a irreducible closed subset? You will show that by showing that that point is in the common 0 locus of the ideal of x. How do you show a point of an lies in a closed subset? You will just have to show that it is a common 0 of the ideal of that closed subset. So all I have to do is I have to take a point small y in capital Y, I have to take its image under psi, which is this, okay, and then I have to verify that this point, the point with this coordinate, these coordinates, satisfies every equation, every polynomial in the ideal of x, okay. So that's what I'll have to do. So let G belong to ideal of x, okay. Let G be in the ideal of x. Mind you, G is a polynomial in n variables, t1, tn. G is a polynomial in so many variables, okay. Then G restricted to x is actually G bar is 0 in Ax, which is just k t1 etc tn by Ix. Obviously an element in the ideal, if you take its image in the quotient, it is 0. But then you see from Ax I have this map zeta. I have started with the map zeta, which is a k-Algebra homomorphism from Ax to Oy, okay. Zeta is what I started with, and zeta is a k-Algebra homomorphism, in particular it is a ring homomorphism, and a ring homomorphism will take 0 to 0, okay. So moral of the story is that if I take 0, which is G bar, under if I apply zeta, I will get zeta of G bar is 0 in Oy. This is what it means, okay. So if I write that down, what I will get is I will get zeta of G bar is 0, which means that but so this is, if you write it carefully, it is G, and what is G bar? It is just G of so you know now I am going to use the fact that zeta is a k-Algebra homomorphism, okay. Zeta of G bar is the same as G of T1 bar etc Tn bar. So I will have to say something. So let me write that again. Zeta of G bar of well, if you want, okay, G T1 bar etc Tn bar is 0, okay. Mind you, G is a polynomial in the T's, G bar is a polynomial in the T bars, okay. G bar is a polynomial in the T bars, and zeta is supposed to take this to 0. But what does zeta do to the T bars? The zeta maps the T bars to the F's. So this implies that G bar of F1 etc Fn is 0. This is what it means. You see, zeta takes T1 bar to F1, okay, and it takes Ti bar to Fi. Then it will take a polynomial in the Ti bars to the corresponding polynomial in the Fi's, okay. Maybe I should just remove this. Maybe I should just remove this bar because the bar is already inside. I should just remove G bar is G of this, just the image of G, okay. I will remove this bar, that is superfluous, okay. So what this translates to is that g of f1 etc f1 is 0 on, and what is this? See, this is what is g of f1 etc f1, it's another regular function on y. See, notice that the fi's are all regular functions on y, okay, and what is g of f1 etc f1? It's some polynomial in expression in the fi's with coefficients in k, okay, and you know, if you write a polynomial in a bunch of regular functions, the resulting thing is also a regular function, because a product of regular functions is regular, a sum of regular functions is again regular, and a regular function multiplied by a scalar is also a regular function, because scalar functions are regular functions which are constant, okay, constant functions are always regular, okay. So this is certainly a regular function and it is 0 in OY, so that means if I evaluate it at every point of capital Y, I am going to get 0. So this will tell you that g of f1 of y etc fn of y is 0 for all y small y in capital Y. This is what it means. A regular function is 0 means if you evaluate it at every point, it has to be 0. But what does this mean? This is the same as saying that the point f1y with coordinates f1y through fny, this point is actually in the 0 set of G, okay. So what I have proved is, but what is this point? This is just psi of y. I proved that for every small y in capital Y, the corresponding point psi y is a 0 of every function g which is an ideal of x, and that tells you that psi lands in x, okay. So therefore this map that you got from y to an actually factors through the closed subset x, so you actually have a map into x, okay. Now the next part of the proof is to show that this map is a morphism, and I will have to show that this map is a morphism, and I have to show that the pullback map that it induces is actually your zeta, and then I would be done, alright. So let's see how to do that. That's also pretty easy to do. Okay, so here is the next claim. The next claim is psi is a continuous map. The next claim is psi is a continuous map, okay. So the situation is like this: I have y, I have psi, this goes into x which is sitting inside an, okay, and I want to show that this is continuous, okay, and mind you, if I show that it is continuous, I am actually more or less done showing that psi is a morphism, because the moment psi becomes continuous, okay, then the only thing I will have to check that psi is a morphism is that it pulls back regular functions to regular functions, but the way we have defined it, it will follow very trivially that zeta is actually psi star, that is alpha of psi. That will be very simple to see, okay. So actually this is the crucial thing that needs to be verified, that it is continuous, okay. So the to see that, that's also pretty easy. Let me think for a moment. Yeah, so let me so it probably involves showing that the pullback under psi is actually zeta. I need that, so let me do that. So let me write that here. Psi induces zeta and psi is a continuous map, okay. How do I explain that psi induces zeta? It's very simple. So you see, alpha of psi, which is psi star, is going to be a map from AX to OY, okay. In fact, I should not say OY, strictly I should say I can define for any map from, if psi is any set theoretic map from y to x, then given any set theoretic function on x I can pull it back to give a set theoretic function on y. So what I'll do is I'll just write maps from y to k, okay. And what is this? This is the usual pullback map. Pullback map exists for any set theoretic map even at the set theoretic level, okay. So you see, if you give me any polynomial h, if you give me any element h which is a polynomial restricted to x actually, then h goes to psi upper star of h, and what is psi upper star of h is just first apply psi and then apply h. This is the map, okay. And what I want you to understand is that what is this map? See, if you take a point of y, h circle psi of y is h of psi y, okay. This is by definition, psi y has been given a definition, this is just h of f1y and so on fny, because that is what psi y is, okay. But this is, if you look at it, h of f1y fny, if you look at this calculation, it is actually zeta of h operating on y, because you see zeta of g is g of f1 etc fn. So similarly h of f1 etc fn is zeta of h by the same argument. So moral of the story is, so this will tell you that psi star, it will tell you that and mind you, so this will tell you that psi star is actually zeta, and it will also tell you that psi star goes just not into maps from y to k, it goes into regular functions on y. O of y is a subset of, this is a set of all possible maps from y to k, okay, just all possible functions, they need not even be continuous, okay. Whereas Oy is very special, these are all morphisms of y into k, they are the regular functions on y, they are very special, okay. And the fact that psi star is zeta, which you have verified pointwise, will tell you that and since zeta takes values in Oy, it tells you that psi star also lands inside, not just in this but in this subset, okay. So this proves that psi induces zeta, okay. So the only thing to show that the zeta I started with comes from a psi here is to show that actually psi is here, namely I should show that psi is actually a morphism, okay. And what is the defining property of a morphism? The defining property of a morphism, there are two conditions. The first condition is it has to be continuous, the second thing is it should pull back regular functions to regular functions. The second condition is already satisfied, the pullback map induced by psi is already zeta, and zeta is pulling back regular functions to regular functions, it's taking every regular function on x to a regular function on y, okay. So it's already pulling back regular functions to regular functions, therefore the only thing that one has to check is actually that it is a continuous map, okay. So that's the reason why I said in the beginning that the essential claim is that it is a continuous map, and once you do that you have proved everything, you have proved the theorem, alright. So how do I check something is a continuous map? I'll have to just check that inverse image of open sets are open, or I have to check inverse image of closed sets are closed, but that's a pretty easy thing, because you see how do you define the Zariski topology on x? What is the Zariski topology in x? How do you define the Zariski topology? You, for example, you specify closed subsets given as zeros of polynomials, okay. So what is a closed subset of x? It's given as a common zeros of a bunch of polynomials, okay. And if you compose those polynomials with psi, okay, those polynomials are regular functions, okay, therefore if you compose them with psi the resulting things will be regular functions on y, and the inverse image will be precisely the locus of those zeros of those regular functions on y, and what you must understand is the Zariski topology given by the Zariski topology on Y coincides with the topology that you get by taking the closed subsets to be common zeros of regular functions. You see, after all, either you can when we started defining the Zariski topology, we always took a set of common zeros of polynomials, but then when we went to a general variety, or which could even be an open subset of a closed irreducible subset, then we had to define regular functions, and these regular functions were locally given by quotients of polynomials, okay, and the zero set will be therefore locally the zero set of the numerator polynomial, which is anyway closed, okay. It has got nothing to do with the denominator polynomial, okay. The zero set of a quotient of polynomials is essentially the zero set of the numerator. The denominator polynomial is anyway assumed to be non-zero, okay, otherwise we wouldn't put it in the denominator. So what you must understand is, if you take a variety, okay, and if you take a bunch of regular functions on that variety, and you take the common zero locus of a bunch of regular functions on that variety, the result is again a closed subset of that variety, just like closed subsets of affine space are given by common zeros of a bunch of polynomials. Closed subsets of any variety are simply given by the set of common zeros of a bunch of regular functions, okay. And so if you start with a closed subset in here, that will be the common zero locus of a bunch of polynomials, okay, and its inverse image here will be the common zero locus of the bunch of regular functions which are pullbacks of these polynomials, and that is again closed. So what this argument tells you is that psi pulls back closed sets to closed sets, so it is continuous and we are done, okay. So let me write that down. Psi is continuous as psi inverse of z of some j is going to be psi inverse of is going to be intersection of okay. So if you want, I can write the full blown set theoretic thing that you might. So z of j is h inverse of 0 intersection where h belongs to j, right. What is a zero set of an ideal? Zero set is, you take this for each element in the ideal, each polynomial in the ideal, look at its zeros, which is h inverse of 0, and you take the intersection. This is the common zero set, and you know psi inverse, taking inverses behaves well with respect to intersection. So this is going to be intersection h belongs to j psi inverse of h inverse of 0, okay. And if you see that this is just the zero set in, this is just the zero set of first apply this is just zero set of h circle psi, intersection of the zero set of h circle psi where h belongs to j, okay, and this is closed in Y. So this implies psi is continuous, and since psi is continuous, it already the map that it induces pulls back regular functions to regular functions, so it is a morphism. And so I have found psi here. I have been able to find a psi. I have been able to find a psi which goes to zeta, and that gives me the surjectivity, and I am done with the proof, okay. So the proof ends here. So the crucial point that you will have to understand is the following, which you can think of as, you know, as a separate exercise if you want. I mean, it's actually, if you understand it, if you have understood it well, it's just a tautology. But take any variety, take a bunch of regular functions, okay, then the common set of common zeros of those regular functions is a closed subset of the variety, okay. It is a closed subset because regular functions are locally quotients of polynomials, and taking the common zeros of such regular functions actually amounts to taking common zeros of a bunch of polynomials, namely the numerator polynomials locally, okay. And that's a fact that you will have to understand, okay. So I will stop here.